In this video, we'll look at the concept of regularization and see what it's good for and how we introduce it into the training of a neural network. So now in describing the full procedure for stochastic gradient descent, we are at the step where we have to specify a regularizer and also how we actually compute the gradients of the regularizer with respect to our parameters. So we see the regularizer is here, so it's involved in how we update the parameters of the neural network. The role of the regularizer is to penalize certain types of functions. And specifically, we will want to penalize neural networks that are very complicated in the sense that they correspond to a function that is very nonlinear and might be able to overfit on the training set, that is essentially learn more or less by heart the information that's contained in the training set and not be able to generalize well to new examples. So we'll first look at a few common regularizers that are used for neural network training, and then we'll try to build some intuition for why it's actually important to use regularization in neural networks. Now, first regularizer that's very common is L2 norm regularization. Typically, we only regularize the weights, so the connection weights between the hidden layers. And in L2 regularization, what we do is that we penalize for each hidden layer and for each connection ij between the jf neuron in the previous layer and the ith neuron in the layer k, we will penalize the square of the weight value. Another way to write this is to notice that this sum here actually corresponds to the Frobenius norm. Actually, it's the square of the Frobenius norm. The Frobenius norm is just the square root of the sum of the square of the elements in the matrix. And so if we take the square of that, that corresponds to this whole sum here. So this is essentially shrinking the weights towards 0 with a squared penalty. The gradient of the regularizer with respect to the weights for the kth layer is actually very simple. It's just 2 times the weight matrix. So as an exercise, you can try to do it, but you'll see it's very simple to obtain, a very easy result to derive. Like I said, usually we only apply it on the weights and not so much on the biases. We don't expect to overfit the training set by changing the biases a lot, and more by changing the weights, which really dictate how the function can become more or less nonlinear and so more or less flexible for overfitting. And for those that are familiar with graphical models and the idea of probabilistic modeling, we can actually think of L2 regularization as a setting where we assume that the weights of the neural network came from a Gaussian prior. So that's because of the square here. If you were to do maximum and posteriori fitting of your probabilistic model on the training set, then you'd have a term which would correspond to the sum, the square of the parameters. So that comes out of assuming that there's a Gaussian prior on the weights. I won't discuss this so much, but this is a notion that people are familiar with probabilistic modeling and graphical models will be familiar with. Then there's L1 regularization, in which case we replace the sum over the square of the weight values with an absolute value. So we penalize the absolute value of the weights. And if we look at the gradient, actually the gradient is only well defined for weights that are non-zero. And so that's because the absolute value looks like this. And so where this would be 0. And so if we're here, we see that the gradient would be negative. So if the weight is negative, then the gradient is negative. And otherwise, if it's positive, then the gradient is positive, and it's actually equal to 1. This is a linear function with a slope of -1, and this would be a linear function with a slope of 1. And at 0, it's not defined, we essentially assume that the gradient is then 0. To be more technical, this corresponds to taking a subgradient. So if you ever see that name, that's just the idea that we just take the gradient of a slope that's below the function locally. And so if we had a function that's flat, it would be below the function at the point 0. So instead of using a gradient which is not defined, we use the subgradient of 0. So if we write this in math, the gradient of the regularizer is going to, with respect to some weights, it's just going to be the sign of the weights. So sign of the weight, that's just we're going to define it as 1 if the weight is greater than 0, and -1 if the weight is instead smaller than 0. And otherwise, the two conditions would not be satisfied, so it would be the sign function would return 0 for the case where the weight is 0. One nice thing with L1, which is different from L2, you don't get this from L2 regularization, is that with a strong regularization, the weights are actually going to be pushed towards being exactly 0. And so at the solution, once the stochastic gradient descent has converged, you'll have a certain number of weights which are going to be exactly at 0, which can be understood as a procedure for pruning away some of the connections between the weights. So with L1 regularization, it's kind of equivalent to learning which neurons should be connected to each other. And then we see also that if we remove connections between neurons, then implicitly that means that the neural network is less complex. So really, by penalizing the L1 norm of the weights, we should be getting a neural network which is less flexible and less able to overfit on the training set. And in this case, there's also a probabilistic interpretation where this is equivalent to assuming that we are putting some Laplacian prior, so Laplacian distribution as the prior distribution for what could have generated the weights of the neural net, which under our assumption has generated our training data. So again, I won't discuss this more, but these are topics that are, concepts that are frequent in probabilistic modeling and graphical models. Okay, so why do we want regularization? And what we really want is not do well on the training set, is actually do well on new examples. For instance, examples that would come, that would be in the test set. And so that's the, we're interested then in the generalization performance of our model. And it can be shown more formally that the generalization error of a learning algorithm decomposes into the sum of two terms, a bias term and a variance term. So the variance of a learning algorithm is essentially a measure of how much would the model vary if I changed the training set. So for instance, if I had an infinite amount of data and I was able to construct many separate training sets, and then I ran my algorithm on these different training sets, to what extent would the model vary between training sets? To what extent would it be different and correspond to a different f function that we're trying to learn? In our case, a neural network. The bias will instead be to what extent is the average model I would be getting by changing the training set and so sampling many different training sets. To what extent would the sort of average model be close to the true solution of my learning problem, that is the true function which I could call f star of x, the true function which really has generated these training samples and is behind any new test example I would encounter and have to do predictions on. And so to get a more intuitive understanding of what this means, here's a cartoon illustration. So, so the gray areas correspond to different neural nets. So each point in a gray area is a neural net that I would be able to obtain for a particular training set amongst all training sets I could sample for a given problem. So these are the possible Fs, the possible neural nets I could be obtaining by training on a given training set. And so for different training set, I'd be getting all of these different neural nets. And f star is going to be the point in my space of function which corresponds to the true solution, the true function that actually generates my my labels that I'm observing. So in this case here, we have low variance because we see that the region of potential neural networks I could get by varying the training set is actually quite small. But I actually have high bias because on average, so let's say maybe that's this point, the average sort of typical neural net I could be getting is actually quite far from the true solution. So for that reason, I have high bias. On the opposite of that spectrum, I have a case where I have high variance, so the region of potential neural networks is actually quite large, but low bias because on average, maybe the point on average would be sort of here, then that's actually quite close to what the true solution is here. So let's think about why this is bad and this is also bad. So this is bad because in a given situation, I get one training set. So I can get a point that's anywhere here, a solution, a neural net that can be anywhere here. So say it might be here, but because the region is large, and I won't be very far from what the average case would be. So that's good, but unfortunately here the average case, because I have high bias, is actually quite far from what would be the best solution, which would be to report the true function. At the opposite case, because I have a high variance for a given training set, I could be very unlucky and get this neural net, or I could get this neural net. Actually, the probability of getting a neural net which is fairly close to the true solution is actually quite small. This region is very small compared to the whole region of potential neural nets I could be getting. So even though on average I might be lucky and get something that's close to here, even though the average neural net, quote unquote, could be close to the true solution, because I have so much variance for a given training set, it's very likely that I won't be in this region. I would be actually quite far from the true solution. So the best thing to do would be to sort of explore a trade-off between low variance and high bias, and high variance, low bias. And so we have a trade-off here, which seems fairly reasonable. So I have a bias because the average case is not close to f star. And I have some variance. So this region here is bigger than that region here. However, I see that, for different training set, I'm always fairly close to what the true solution might be, the f star. And so back to the idea of regularization, the amount of regularization which is controlled by the lambda weight, which is multiplied by the regularizer. So it determines how important I think it is to minimizing the regularization penalty. By changing for different values of the lambda hyperparameter, I can essentially control whether I'm in low variance, high bias region or high variance, low bias region. If the lambda, the penalization under regularization is very high, then I'm going to get very little variation because I can only explore neural nets that have very small weights, and there are fewer neural nets. We can't count them, but essentially the region of neural nets with small weights is much smaller than the region of neural nets with small and big weights. And so with a big lambda, I'm in the low variance region. But with a small lambda, then I'm in the high variance region and low bias region. And so by trying different values of lambda, I'm able to explore this trade-off between bias and variance, and hopefully get a lambda that provides the best trade-off and better generalization. So this is the idea behind generalization and the use of regularization in neural nets. And so now we know how to introduce two different regularization, L2 and L1, into neural network training.